Isomorphism theorem, but remember from previous session I was warning you what some authors call the first isomorphism theorem, namely this one, which I'll get to in a minute, is not necessarily what other authors. There's no real consensus yet on this. It's a bit confusing and a bit annoying, but be warned. Okay, you may read another textbook, different author, and you'll say, "Hey, well, that's not the first isomorphism. That's the second, or whatever." Right? So there's no consensus. All right. So what is Theorem 64? Well, I put it here in a rectangle to highlight it. It simply says, if you have a homomorphic mapping F between two groups, G and H, then if you form the quotient group of G with the kernel of that mapping, that homomorphic mapping, then that quotient group here is isomorphic to the image of F. And remember, image of F, what does that mean again? It's just the set of all the different elements that these cosets map to. Right? Remember, if two cosets are the same, like if you have x, if you have xk equals yk, then we had theorems about that. Then x and y belong to the same coset. All right. Okay, so there's the statement in shorthand form of the first isomorphism theorem. So the quotient group of G formed from the kernel of your mapping function, your homomorphic mapping function F, is isomorphic to the image of F. These images, if you like, these elements, and they're all different. And you've got this one-to-one mapping of a coset to a member of your image of F. All right. Okay. So that's the statement of the theorem. Now we start the proof, and we will again pull in various strands of theory from the past. Okay. So let's see. Okay. So we know that the kernel is a normal subgroup. Right. Proved that in the past. So that means we can form a quotient group from this kernel, because the kernel is a normal subgroup. And here's the quotient group. So it's your big G, the group you start with, right? Slash divided by the kernel, in a sense. Okay, so that will be a quotient group. And because that is a group, it's a quotient group, so it's still a group. Okay. Because this is a group, then under a homomorphic mapping, if you map from one group, from one set to another, and if your starting set is a group, then your target set is a group. Now I'm throwing that at you. We actually proved it, maybe not explicitly, but very close, in the first exercise of the previous lecture. So what would be lecture 18? Is that right? Let me just check quickly. Let's see. Yeah, so we actually proved it last time. So exercise 18 was the first question. So let F that maps G to H be a homomorphism of a group G to a group H. Prove that the image of a subgroup of G is a subgroup of H. So from the previous lecture, I actually proved that. So let me state that again. If you have a homomorphic mapping, if you're mapping F here, if it's homomorphic, and you're mapping from a group, your starting group into this set, that set is a group. Now, we did it, what I've just read out. Here's a reminder. This was our first problem-solving exercise in the previous lecture. And to remind you, this is just a reminder, so you've seen this before. So if you have a group, G, and it maps into a set H under a homomorphic mapping F, then the subset of G, call it S, right? It will map homomorphically into a subset, call it T, of H, and the point of the exercise was to prove that this subset T is in fact a group, so it would be a subgroup of H, right? And we actually did that. So if you are forgetting a bit, go back to the previous lecture, go back to lecture 18 on the problem solving session towards the end, and have a look at that proof. Okay? Now, so what? Why is this being brought in here? Ooh, look, I'm getting really hot, despite the noise. I'm going to turn on the air conditioning again. Maybe a little bit noisy, but I'm starting to really sweat. It must be 30. It's what, 7 a.m. in the morning. The sunlight's streaming in, and it feels like 35 centigrade already. All right. Okay. So what's the point of saying this? Well, subgroups include improper subgroups. In other words, the trivial group, which is just the group of just one element, which has to be the unit, right? So that's the only group of order 1, because it only has one element. And the other improper subgroup is the group itself, right? So in proving if S is a subgroup of G, then T is a subgroup of H. That includes the special case when S is an improper subgroup, right, of two kinds. Either the group consisting purely of the unit element, or, only two possibilities, or the whole group itself, you know, all of G. Okay, so now we've proved that if S is a subgroup, then T is a subgroup. All right, well let S be the whole of G. Well, that means then T will be H. So if G is a group, then H is a group. Follow that? All right. So in a sense, that was rather implicit, but in fact, we didn't spell it out. But that proof, as in the problem-solving session, we actually proved this. Okay. So given that this is a group, this is a quotient group, so it's a group. Okay. And it maps homomorphically to here. Therefore, this is a group because of this. Right? So this is a group. Right? All right. Now we can start getting onto the proof itself. And to do that, we pull two theorems from the past together. We use a Theorem 57, which I have summarized here to remind you. And Theorem 57 was about equivalence classes. Okay? And the other strands, we're pulling in two theorems from the past. And the other one is Theorem 63, and Theorem 63, which I've summarized here, is about homomorphisms. That's much more recent, right? Okay, so a bit of a reminder. Theorem 57. What's it saying? Now it's about equivalence classes. Well, just briefly, what is an equivalence class? You could replace the word class by subset, right? It's just a different word for the same thing. So you could be talking about equivalence subsets. Now, an equivalence class is what? It's a subset, all of whose members are equivalent to each other. So you take any pair of members, elements of that subset, and they will be equivalent to each other. Right? So Theorem 57 is about these particular kinds of subsets, equivalence subsets or equivalence classes. And Theorem 57 says the equivalence relation, wiggle, tilde, like this, one sine wave, right here, is defined if f of A equals f of B. In other words, if that's true, then A and B they're equivalent. Right? So they will belong to the same equivalence class, the same equivalence subgroup. Now, Theorem 57 says, I hope you can remember this, you can map, and this mapping was bijective, right? It was one-to-one. So surjective and injective, right? Definition of bijective. So what's this? What's this set here? Well, you probably remember at the time scratching your head a bit, saying, "Where'd that come from?" Well, now you're more familiar with this slash, right? So we're talking about a quotient group here. So and if you're remembering this, you're probably saying, "Hey, that sort of looks like this." When we were talking about fibers, right? Can you remember what a fiber was? Now, in the context of talking about quotient groups, these bands here, 1, 2, 3, 4 of them that I've drawn, these bands here are cosets. But if you go back to when we're talking about equivalence classes, these bands here are equivalence classes. Okay, so every element in each band is equivalent to each other. So if you had in this band here, this equivalence class, two elements A and B, then A would be equivalent to B, right? So it looks as though there's something very closely related between equivalence classes and cosets, right? And that's the case. In the case when your F is a homomorphism, right? Right. So this here, what is it? Well, it's these it's these things. But in this context, in the context of Theorem 57 and equivalence classes, these bands here, these subsets, you're not looking on them as cosets, you're looking on them as equivalence classes. So each band is a different equivalence class. Okay? So the set of them is this. So this here, now you're mapping from this set to this set, and this set here is the set